In this video, we will try to interpret the line integral of a vector field graphically. So we're given a picture of a vector field here, and we're given several paths, which in this case are all straight lines. And for each, we're trying to determine not the value of the line integral, that would be too hard to do just looking at it, but just in general whether it's positive or negative or maybe zero. So let's look at the first path in part A, from 1, 2 to minus 1, 2. So starting here and ending here. So the path goes like this, from right to left. So we're going this way along that line segment. Okay, so what I'll do in this video is I'll try to color the path green when the vector field points in the same direction as the velocity of the curve, and red if it points opposite. So here the whole thing is going to be green, because if you think about it, the velocity vector for this curve will just always point to the left. Since as we move from right to left, we're just going in a straight line horizontally, so the velocity vector of this curve is always just going to be an arrow pointing to the left. And how we interpret how the line integral of the vector field is going to evaluate, we need to think about what the dot product of this velocity vector is with the vector field itself. So at each point on the curve, imagine you draw the velocity vector and take the dot product with the blue arrow at that point. So here it would be positive because both arrows are pointing more or less to the left. Or in other words, the angle between them is acute. It's less than 90 degrees, so the dot product will be positive. And it'll be the same thing all along the curve. Even over here, when the arrows are pointing down, the angle is still acute. It's less than 90 degrees, and so the dot product will be positive. So in fact, the dot product of the velocity of the curve and the blue arrows will be positive along the entire path. And so here, the line integral will be positive. Okay, let's look at part B. The line segment from, okay, let's maybe erase this. The line segment from minus 1, minus 2, so here, let's start in black, starting here, to 1 comma minus 2, so ending here. So we're going like this now, from left to right. So now our velocity vector of the curve is always just pointing straight to the right. So now, if you imagine that, let's say at this point, and draw the velocity vector of the curve, it points to the right. Now the angle between that velocity vector and the blue arrow is obtuse. It's more than 90 degrees. So the dot product of those vectors is going to be negative, since they're pointing in the opposite direction. So here I'm going to color it red. So the velocity is always pointing to the right, but the arrows in the vector field are pointing to the left. The angle between them is always going to be more than 90 degrees, so the dot product will be negative. And that's true all along the curve, so everywhere that dot product is negative, so we're integrating a negative function, so the answer is going to be negative. Okay, let's look at part C. part C, we go from -2, 2. So that's all the way up here in the corner. To -2, -1. So to here. So we're moving vertically straight down. So that's the path. So here, the velocity vector of our curve is always pointing down. So we need to imagine taking the dot product of all the blue vectors along the path with a vector that points straight down. So as you can see, it's going to be positive all the way here above the x-axis. So until we get to y equals 0, all of the arrows are pointing mostly downward. So we'll get a positive dot product. But as soon as we pass that threshold and go down here, the arrows are pointing more up. And so the angle between these arrows and our velocity vector is obtuse, giving us a negative dot product. So part of the path, we're integrating a positive function, and for the end part of the path, we're integrating a negative function. So think back to Calc 1. You're integrating a function which is positive and then negative. But if you look at it, the positive part is longer than the negative part. It's positive for 2 units, but negative for only 1 unit. So think back to Calc 1. If you integrate a function that's positive for some of the time and negative for some of the time, the areas cancel out, but there's more positive area than there is negative. So in the end, the positive part wins out. Again, I repeat, we're integrating a function that's positive and then negative, but there's more positive. So the negative part cancels out some of the positive, but not all of it. So in the end, the positive part wins out. Now finally, let's look at part D. It goes from 2, -1 to 2, 1. So 2, -1 looks like it's here to 2, 1, which is here. So we're going straight up. So now our velocity vector is always pointing straight up. So as you can see, for the first part of the path, the arrows are pointing down, so the dot product will be negative. And for the second part of the path, the vectors point up, so the dot product will be positive. So a very similar situation to what we had in the last part. But now the difference is, it looks very symmetrical. The paths have the same length. There's equal amounts of positive and negative, and so they should cancel each other out. So again, think about in Calc 1, if you have a function like this, where it's positive for some of the time and negative for some of the time, and imagine that these two parts are actually the same size. So the positive area and the negative area are the same, then they'll cancel each other out and the integral would be 0. And so that's what happens here. This is actually exactly 0.